Welcome back to The Explainer. Today, we're unpacking something literally game-changing. We are looking at a 2026 paper that introduces a novel framework called FQ-SHAP. What is absolutely fascinating about this research is how it takes a mathematical concept from all the way back in the 1960s and uses it to finally make quantum computing understandable in plain English. If you've ever felt like quantum circuits are just this impenetrable wall of complex math, you're going to love what we uncover today.
Here's our roadmap for today. We're heading 1. The quantum black box. 2. The problem with crisp scores. 3. Enter fuzzy logic. 4. How FQ-SHAP actually works. 5. Solving the entanglement paradox. And we'll wrap up with 6. Human-readable quantum circuits. Let's get right to it.
Section 1. The quantum black box, the growing opacity of quantum computing. So, as quantum computing rapidly scales up, we're seeing these circuits become incredibly complex black boxes. And the problem? They entirely resist manual inspection. You literally can't just glance at the code and intuitively know what each gate is doing to the overall system anymore. Moving to Section 2. The problem with crisp scores, why current AI explainability fails quantum mechanics. To actually figure out what's happening inside these quantum black boxes, researchers have been relying on a framework called Q-shap. And look, Q-shap is great, but it has a massive limitation. It relies entirely on rigid, inflexible mathematical rules, or as it's known in the industry, crisp logic.
Here's the crucial point. Crisp logic blindly keeps or deletes quantum gates based on hard black and white numerical thresholds. A gate either crosses the line and lives, or it gets trashed. There's no nuance whatsoever. Fuzzy logic, on the flip side, categorizes behavior using degrees of truth. It's kind of like asking a toddler if they're tired. It is almost never a simple yes or no. Fuzzy logic evaluates the system exactly how a human expert would.
Section 3. Enter fuzzy logic. Embracing the gray area of quantum mechanics. To get past those super rigid limitations, a brand new paper introduces FQ-SHAP or fuzzy Q-shap, which completely ditches the binary thresholds to fully embrace the nuanced reality of these circuits.
So what actually is fuzzy logic? Well, it's a mathematical approach designed way back in 1965 by Lofty Zadeh. Instead of saying something is strictly true or false, just a 0 or a 1, it maps numerical values to degrees of belonging. So a gate's importance isn't just important or not important. It could belong, say, 80% to the critical category and 20% to the moderate category. By applying these degrees of truth to quantum logic, FQ-SHAP flawlessly bridges the gap between really heavy math and practical, graded human insights.
Section 4. How FQ-SHAP actually works, the 5 pillars of fuzzy explainability. Let's see exactly how this framework maps human-like reasoning right onto the quantum flow. The researchers integrated this at 5 distinct levels. First, they classify gate importance on a scale from negligible to critical. Second, they weigh the consistency, meaning if there's a disagreement on critical gates, it's penalized way more heavily. Next, they use a Mamdani fuzzy inference system to actually decide which gates to prune. Fourth, they classify the roles of the qubits themselves. And finally, and honestly, this is the real magic here, they generate explanations in natural language. So how does this process build step by step? Step 1, FQ-SHAP grabs the raw numerical data, specifically the gate fidelity importance and its contribution to entanglement. Then step 2, it fuzzifies those inputs. It literally asks, is this low, medium, or high? Step 3 is where it gets incredibly smart. It passes these fuzzy memberships through 6 expert rules to jointly reason over a gate's overall physical importance. And finally, step 4, it spits out a highly clear recommendation: keep it, prune it, or mark it as uncertain for further review.
You might be wondering, why go through all this trouble? Well, this exposes a massive flaw in crisp logic. Algorithms will frequently tell us to delete a seemingly low-performing, useless gate based strictly on its fidelity score. But here's the catch. Sometimes, that useless gate is quietly doing the heavy lifting of creating quantum entanglement for the whole circuit. If you blindly delete it, you accidentally destroy the circuit's entire quantum computational power. And no one wants that.
Which brings us to Section 5, solving the entanglement paradox, saving the hardware efficient and Grover circuits. We have 2 incredible examples of this in action from the source paper.
The data here brilliantly illustrates what we were just talking about. For a hardware-efficient VQE circuit, there is a specific CNOT gate that has a terrible standard gate importance score, just 0.12. A crisp logic system would immediately throw this gate straight in the trash. But FQ-SHAP safely keeps it. Why? Because the fuzzy rules recognize that while its fidelity is low, its entanglement delta is a massive 1.0. It is literally the sole entanglement-creating gate in the entire circuit, and FQ-SHAP's multidimensional reasoning protected it.
We see a similar but even more complex paradox solved with the Grover search algorithm circuit. The wild thing is, this circuit ends with zero entanglement in its final state. So, a basic algorithm looks at the end result and thinks, hey, no entanglement here, let's delete the CZ oracle gate. The importance score is low. But FQ-SHAP preserves the CZ oracle gate anyway. It does this because it tracks the step-by-step evolution and spots a massive transient entanglement spike right in the middle of the computation. FQ-SHAP catches exactly what crisp logic completely misses.
Section 6. Human-readable quantum circuits. Translating quantum math into plain English. The mechanics under the hood are vastly superior, for sure. But the ultimate triumph of this framework is what it actually hands back to you, the user, at the end of the process.
Instead of handing you a matrix of impenetrable math and shapely values, the system translates its fuzzy rule base into hedge-qualified natural language statements. Statements like this one from the paper. The fidelity-based analysis classifies this gate as weakly moderate. It contributes high entanglement. Pruning recommendation, keep. It literally speaks to you like a colleague. Meaning, you absolutely do not need a PhD in theoretical physics to audit a quantum circuit anymore.
Now, when you zoom out to the global summary across all 5 benchmark circuits, you uncover something amazing about the final pruning recommendations. The data just proves the sheer efficiency and power of this new fuzzy logic approach.
Across the 5 tested circuits, which included Bell State, GHZ, Grover, hardware efficient, and teleportation, the framework confidently recommended pruning away an incredible 62% of the total gates. It identified that nearly 2/3 of the operations were mathematically negligible or minor.
But here's the kicker. Despite aggressively throwing away well over half the circuit, it achieved a 100% accuracy rate in successfully identifying and keeping the vital entanglement-creating gates. Absolutely high efficiency with zero catastrophic deletions. Ultimately, what this research proves is that as quantum circuits scale toward real practical advantage, the gap between numerical explainability scores and actual actionable human understanding is going to widen dramatically. By translating complex quantum metrics into the linguistic framework that our human reasoning naturally operates in, FQ-SHAP beautifully bridges the gap between hardware scale and human comprehension.
And it leaves us with a truly fascinating thought. If we can successfully teach algorithms to explain the dense, super unintuitive black box of quantum physics in plain English, what other complex technological black boxes can fuzzy logic illuminate next? As computing bleeds further into the unknown, will embracing the gray areas of fuzzy logic be the ultimate key to keeping artificial intelligence and future tech understandable to us? It's a thrilling prospect. Thanks for joining me on this explainer, and keep questioning those black boxes.